Today, we want to keep looking at integrals. Today, we're going to go back to double integrals, but we're going to start using polar coordinates. Remember, the big idea is we're trying to describe a region because we need to tell the integral what values of x and y to plug into our function. Today, we want to go back, we want to look at double integrals, but we want to look at functions that are in polar coordinates. A lot of functions with round stuff in it is much easier to describe if we start using polar coordinates. So let's remind ourselves of what polar coordinates, how polar coordinates work, and then talk about how to describe a region in polar coordinates. It's going to work the same. We're going to say what's x between and what's y between. And then in polar coordinates, we're just going to say what's r between and what's theta between. There is one small thing that we have to worry about. Let's first remind ourselves of about how polar coordinates work. When we have rectangular coordinates, we have the horizontal and vertical distances from the origin. So the coordinates at this point, x, y. X is just the horizontal distance to the point and from the origin, and y is the vertical distance from the point to the origin. That's just one way of describing a location in R2. So these are rectangular coordinates. We could also describe this location in R2 with one distance and an angle. So we could describe this point as being this distance from the origin, we call R, and an angle theta measured from the positive x-axis, where counterclockwise is the positive direction. So these coordinates could also be the points r and theta. It's R2, so we need two coordinates. But in this case, only one of them is a distance, the other one is an angle. We can translate between the two. So we can, if we have rectangular coordinates, we can calculate polar coordinates. And if we have polar coordinates, we can calculate rectangular coordinates. So notice that we're just looking at a right triangle. At least in the first quadrant, we can just start worrying about this, or look at this right triangle. And we'll see that the sine of theta is y over r. So sine theta is y over r. And so that tells us that y is equal to r sine theta. So if I have polar coordinates, I can figure out the y coordinate by taking r sine of theta. And cosine of theta is adjacent over hypotenuse. And so I can calculate with r and theta, I can calculate x as r cosine theta. In the other direction, I can use the Pythagorean theorem if I have x and y to figure out r. So r is the square root of x squared plus y squared. And then if I need a relationship between theta x and y, since y is opposite and x is adjacent, I can use the tangent. So theta is the tangent inverse of y over x. We might have to do a little bit more work. Tangent is not invertible all the way around the circle. So we may have to do a little more work to make sure that we get the theta in the correct quadrant. So we may just be looking at a reference angle if our theta is in the second or third quadrants, because the tangent is only invertible from -90 to 90 or negative pi over 2 to pi over 2. So we may just be getting a reference angle. And we'll have to make sure that we'll put it in the second or third quadrant, depending on the values of x and y. Polar coordinates are pretty handy. If, for example, we want to describe a circle, this is probably the same example everybody uses. If I want to describe this circle in rectangular coordinates, we know we can't make a function out of it. The circle, let's say, will be x squared plus y squared is equal to 3 squared, or 9. I'm going to use the same circle I was using yesterday. So describing that circle with rectangular coordinates, I don't get to use a function. No matter which variable I try to solve for, I have to end up with two functions, the plus and the minus. But in polar coordinates, we're just describing all the points that are 3 units away from the origin. So here's the equation in rectangular coordinates. Not able to write a function. But in polar coordinates, we can write a function. So we do get to write a function in polar coordinates. So handy sometimes. One of the things that makes polar coordinates a little bit tricky is that we have spent a lot less time looking at functions in polar coordinates than we have in rectangular coordinates. So we don't have this kind of deep library of functions that we've built up the same like we have with rectangular coordinates. And it's the same thing when we start talking about equations, graphs of equations after graphs of functions. We spend so much time thinking in terms of functions. We have less experience, and we have a smaller library of equations that we can describe. So it's just a matter of gaining experience and getting mileage. Our goal today is to integrate a function in polar coordinates, set up a double integral for a function in polar coordinates. Let's remind ourselves what we need for a double integral. So we're integrating a function, f, over a region. And we can think of this as a volume where f is a surface and we're just trying to figure out what values of x and y to plug into the function. And then we multiply the height by the area. So the dA is a little slice of area. It can either be dx dy or dy dx. And so we're thinking of dA as a small piece of area. So the dA it's an area where we have a dx times a dy. We have a length times another length. I could call one of them width, I guess. But they're both lengths, or they're both widths. So the dx, it's a small change in x, is a length, and the dy, a small change in y, is a length. So when I put them together, dx dy, I end up with an area, because I have a length times a length. So for a function of x and y, that's no problem. Then we just have to describe r by saying what's x between and what's y between, and those are the values that we plug into the function. Here's where we run into a problem. Need to draw a picture of it. So if we look at some a point and think in polar coordinates, if we say take this point and we're going to think in polar coordinates, we can take a little piece of dr, a little change in the radius, and then the other piece will be a little change in the angle, d theta, dr and d theta, just like we had dx and dy. The problem is, I'm going to put a d theta in here. The problem is dr times d theta is not going to give us an area, because d theta is not a length. D theta is a change in angle. It's going to have some, it's going to be measured in radians, and that's not length. So dr is length, no problem. D theta is not length. So I can't just set up dA as dr d theta. So that's a problem, because when we try to write dA, if we just write d theta dr d theta, dr is length, but d theta is not length. So that means that dr d theta is not going to be a dA. It's not going to be an area. What we want is a little chunk of area So I want that to be a length. And I'm going to straighten this out, because if d theta is small enough, this is not that curvy. But we're looking at this small piece of area. And this is what we want to be our dA. But we can't just set it up as dr d theta because dr is length and d theta is not. We would only have length. We'd only have meters to the first. We wouldn't have meters squared. So what we have to do is somehow make the d theta into a length. And we're going to do that with the arc length. Now, d theta's the length of d theta, this arc length, will depend on how far we are from the origin. And so this length, I didn't give myself enough space. We're just going to use the arc length as one side of this little square, and then we'll use dr as the other side of this square. I know it's not a square because those d theta sides are curvy, but if we make it small enough, it'll be very close to a square, and that's what we need. It's going to be infinitely small pretty soon. So we want to calculate the arc length, and arc length depends on not just the angle that we go through, but how far we are from the origin. So I'm going to need the distance, and then I'll multiply the distance by the change in angle. So one side is going to be the arc length, and the other side is going to be the dr. So our not quite square dA is not quite a square, but it's really tiny, so it'll be very close. So dA is not quite a square, but it's very close because it's so small. So I'm going to read it, I'm going to imagine it as a square where one side is dr and the other side is the arc length, which is r times d theta. And that's what we're going to use for dA. So dA is going to be r d theta times dr. We want to be able to switch the order. The r is just going to be pulled into the function. That's going to be something that we're going to need to integrate along with the function. But the dr and the d theta we can put in any order we want. So we can also write it as r dr d theta. But we need to remember that that r is part of the dA. So we're turning d theta into a length by multiplying by the radius. We're just calculating the arc length. And then we're thinking this little piece, if we make it small enough, will be close enough to a square. And we wave our hands at it a little bit. Say the magic incantation of calculus, close enough. And then just integrate with an extra r in our function. Now, we need to make sure that this works. And for that, it's a good thing that we have enough of a library of functions to integrate something both in rectangular coordinates and something in polar coordinates. So if we imagine that circle that we had before, we know that the equation of the circle is x squared plus y squared is equal to, I'm going to use 3 again, to 3 squared. We can calculate the area of the circle. We know what the area of the circle, it's pi times something. There's some pi involved. We can set up a double integral for the area of this circle by integrating the function 1 over this region, and we'll just use this whole region as R. So let's set up a double integral for the region. We're going to integrate the function 1, and we can integrate it to dx, dy. So starting with the outer integral, the y values go from -3 to 3. And the x values go from negative square roots of 9 minus y squared to positive square roots of 9 minus y squared. So now we'll integrate this function with respect to x and then plug in the endpoints. So I still have the integral from -3 to 3. The integral of 1 dx is just x, and I still need to evaluate that from negative square root to positive square root. So I need to plug in the negative square root and the positive square root and subtract. That's going to give me 2 copies of the square root of 9 minus y squared. And we still need to integrate this from -3 to 3 dy, which is almost exactly the integral that we would have come up with if we were in single variable calculus and we wanted to find the area of a circle. So here's the problem that we run into. We have to do some trigonometric substitution, so we're kind of sad about that. But if we were going to integrate this by hand, that would be where the trigonometric substitution goes. But we know that the answer is going to be pi r squared, so the answer is going to end up being 9 pi. Arc signs are where the pi's are going to show up. So I put the 2 square roots of 9 minus y squared come from the fact that I plug in the plus 9 minus square root and the minus square roots, and I subtract them. I'm just evaluating the definite integral. So the definite integral part, I evaluate x at the positive square root and the negative square root and then subtract. So I have plus square root of 9 minus y squared and minus the square root of 9 minus y squared. And we're subtracting them. So that means we're adding them. And so I end up with the 2. So in rectangular coordinates, this calculation can get messy. It's one that we already know. Coming up with 9 pi wasn't the point. trying to fit this round thing into our square coordinates and seeing that as messy, that's the point. Now, if we write the problem in polar coordinates, we saw before that we do get a function. This is just in polar coordinates, this is just the equation r equals 3. And we just need to integrate it all the way around the circle. So in polar coordinates, I thought I had enough space and I was wrong. In polar coordinates, this is the equation r equals 3. And we just want to make sure that we go all the way around the circle. So when we set up a double integral, if we're going to set it up in polar coordinates, we still want to integrate the function 1 to find an area. But dA is not just dr and d theta. dA is r dr times d theta. So I need r times d theta for the length, and then the dr. So I can write r d theta dr or r dr d theta. The r, we're finding the area. The r needs to go from 0 to 3 because we want to get all those values. R equals 0 to r equals 3. Remember, we start from the origin. R is the distance from the origin to the point. And we want to make sure that we go all the way around the circle. So we just want to run theta from 0 to 2 pi. The area part comes from setting up d theta as r d theta instead of just d theta. D theta on its own does not give us a length. We use the arc length formula and multiply by the radius to turn d theta into a length. Apparently I closed my notebook while it was still damp. Now our calculation, it works the same. We're instead of integrating just the function 1, the r from the dA gets lumped in with the function as the part that we integrate. So the integral of r with respect to theta so we first integrate with respect to theta. The integral of r with respect to theta, since r is constant, is just going to be r times theta. And then we'll have to evaluate from 0 to 2 pi. We still haven't integrated with respect to r. So we plug in 2 pi and we plug in 0. So we're going to have 2 pi, or r times 2 pi minus r times 0. So that's just going to be 2 pi times r. But we still need to integrate the r. So this is dr from 0 to 3. So 2 pi r, and with respect to r, is going to be pi r squared, evaluated from 0 to 3. And that'll give us 9 pi. just like we suspected. Any questions? One of the things we want to think about with polar coordinates is that polar coordinates, setting up things in polar coordinates is just another tool in our mathematical toolbox, and it's better to have more tools than to have less tools. You wouldn't want to try to build a set of tools and say, well, I don't need a screwdriver. I'll just go with nails all the time. That's just choosing rectangular coordinates and just always just using nails. Even though there are some things it would be better to use screws. Better to have more tools than it is to have fewer tools. And if you're like, oh, well, I'll never need polar coordinates, you are actually arguing that you don't want to know something. And if you don't want to know something, why are you in school? You know what I mean? It's just a weird argument to make. Because you're thinking, I don't need this information. At which point I might call, dude, you're over 18. School is entirely optional now. From that standpoint, you don't need any of this. You're here because you want to know things. At least that's, in my view, why you should be here. You should be here because you want to know things. I don't like the idea of threatening people to know stuff. I think that's just super destructive. It also bugs me that when schools get together and faculty get together and we start having discussions about cooperating with like the outside world, the business world, like cooperating with industry. Thank you. I knew there was a word for it. Cooperating with industry. And I don't think I really want to cooperate with such an exploitative machine. Why do we want to help industry exploit its workers? You know what I mean? So, yeah, I don't want to call up industry and say, hey, what kind of worker would you like us to churn out? Because honestly, if schools did what I want them to do, what I think they are built to do, and turn out thinking people who can solve problems, industry will be like, well, no, not like that. All of our workers are thinking and having ideas, and they're realizing that they're being exploited by us. And now we have a problem. Could you not teach them that? Could you not give them those kind of ideas? We just want you to train them for free. That's kind of what we're going for here. You know what I mean? It's kind of one of those things that happens. I don't know how many of you are, I know some of you are working. I don't know which ones are working. If the company that you're working for is going to demand that you go back to school and get a degree, make sure that they're going to pay for it. If they're not going to pay for it, leave that company immediately. As soon as they say we need you to get a degree, we're not going to pay for it, go. They don't want you. They're trying to get rid of you. So go. Just say, I understand. Here's my letter of resignation. Find a company that will pay for your schooling, that if it's going to require that you get it. You know what I mean? So at a certain point, industry said, we want people to have college degrees. And so everybody's like, all right, let's get college degrees. And then industry was like, oh yeah, starting salary, $10 an hour. I know you're $250,000 in debt, but and then what happens is that the college is actually schooling actually works on some people, and they realize, hey, this college thing is a bit of a scam. It's just a vehicle to put me into debt so I can owe someone money forever. I don't know if you're familiar with the line from the song. Don't call me because I can't go. I owe my soul to the company store. This is just the new company store. You know what I mean? Anyway, polar coordinates. Now, there are certain situations where polar coordinates are going to be super inconvenient. So for example, just from the more tools in the toolbox aspect of things, if I set up something with a lot of flat sides, like a line, but it's got this vertical vertical side, we could set this up in polar coordinates. Theta goes from 0 to 45. Let's just put this at 3, 3. So no problem for theta. Theta goes from 0 to pi over 4, 45 degrees. But the radius is a bit of a problem here. The radius at the top here is 3, but the radius here at the bottom is the x coordinate. So x is, and since x is equal to r cosine theta, if I solve this for r is x over cosine theta. So my radius starts off at x secant theta and then goes up to 3. So for round things, we'll have our polar coordinates in our toolbox. And for things with flat sides, even though we could just use the hammer on this problem, we might say, hey, why don't we grab a screwdriver for this problem? Because you can use a hammer on a screw. You'll do all kinds of damage, and it's not going to be as effective. But there are better tools for the job. Any questions? Comments? Snide remarks. On that note, having more tools is better. I'm pretty sure that college is not the one-size-fits-all tool that we think it's going to be. So there used to be more tools in the toolbox, but we decided that we didn't want to pay for those. And it's like, well, let's just do this one thing. And that's at that point, it's like we say, let's just use rectangular coordinates all the time. And then we're like, well, dude, everything is round. And it's like, well, meh. Anyway, that's all beside the point. I just want to do inception on you put some different ideas in your head, challenge the status quo of everybody has to go to high school, all high schools have to be college prep because everybody has to go to college. I think that's a dumb idea. That is literally just taking options off the table. Actually, not literally taking options off the table. I shouldn't use literally if they're going to be like all on the table. But then again, literally is just for emphasis now. Language has evolved. This is why I like math. Math is just math. We add to it. The words mean things. Anyway, that's all beside the point. So check out 16.4 is where we're talking about double integrals and polar coordinates. Then we also want to talk about triple integrals. We have two kinds of weirdo round coordinates, cylindrical and spherical. So we need to set up triple integrals in those coordinates so that we have more tools so that we can approach more problems. Once we have all this in our tool bag, then we get to move on to vector valued functions. So that's going to be another big shift. All right, but that's going to do it for today. I'll see y'all on tomorrow. Actually, I'll see y'all on Thursday. Tomorrow is a flex day. So I'll see y'all on Thursday. Everybody have a good couple days. And thanks for playing.